Since the E1 reaction proceeds through cationic intermediates, it's reasonable to expect it will proceed well only with secondary and tertiary substrates, which would give reasonably stable cations. And one might wonder, well, do primary substrates undergo elimination reactions at all? And the question is yes, but as you probably might expect, they do that through a different mechanism known as the E2 reaction. And the difference between E1 and E2 reaction is relatively similar to the difference between SN1 and SN2 reaction, in that E2 reaction is elimination bimolecular, which means that the rate law involves not only our substrate, but also the base that is used to deprotonate. The other consequence of the rate law is that it's a single-step reaction in which both base and substrate participate in the rate limiting. To show this on an example, if we have a relatively strong base, such as a hydroxide, this base does not necessarily need to wait for the cation to be formed, especially in the case of this primary bromide. It can abstract the proton right away, which then leads to formation of a double bond and subsequent elimination of the leaving group, to finally yield water, Br-, and ethylene. And so this is sort of a case where you have a base which is significantly stronger than it was in an E1 reaction, and it simply can't wait for the cation to be formed. Instead, it jumps in, takes the proton from the neutral substrate, and then gives the elimination. Furthermore, the E2 reaction does not apply only to primary substrates. Because the attack of base occurs onto a hydrogen, which is sterically very undemanding, and not onto a carbon, E2 reaction, so the synchronous mechanism, can happen just fine in tertiary systems as well. And so we can have a scenario where we eliminated the bromide and get this alkene plus water plus Cl-. In this case, the reaction is not even hampered by SN2 reaction because SN2 cannot compete since it's too crowded on carbon, so the reaction actually works better for the tertiary substrates. In cases of primary substrates, there's competition with SN2 reaction, as expected. Now, in cases, the E2 elimination occurs through the reaction coordinate that you're already familiar with, so it's a single-step reaction. Everybody is involved in that one rate-limiting step. But the interesting difference between E2 and SN2 reaction, although they share some similarities, that the E2 reactivity order is completely opposite from the one observed in the SN2 reaction. So tertiary substrates are the most reactive, followed by secondary, followed by primary. And this is all guided by alkene stability. Because as we know, the tertiary substrates will probably give the most substituted alkenes, the most stable ones, and that'll be the case as we go towards the fact. Zaitsev's rule again applies to E2 elimination reactions as well. So in cases we have a potential mixture, we will get the more stable alkene, such as treated cyclohexyl methyl bromide. With hydroxide, we will get this as well as this, but this will be the major product. And so the E2 reaction is the final of the four reactions that halogen alkenes undergo through, and its comparison with E1 reaction is particularly indicative because E1 requires a weak base, secondary or tertiary substrate, whereas E2 is sort of it's a different mechanism where base is strong enough so that it doesn't have to wait for the formation of cation, and just jump in and then do the reaction right away, and both tertiary, secondary, and primary substrates will work in this case. In the next subtopic, we will see that Much like SN2 reaction, which is occurs in a single step, and therefore is stereochemically very well controlled, the E2 reaction, which also occurs in a single step, exhibits significant E2 control, significant steric control over the product outcomes.